Hi, good morning to all. This is Wahida, and today I am discussing about micro instructions. Okay, micro instructions. So, having described a scheme for sequencing micro instructions, took we now take a closer look at the format of individual micro instructions. A straight forward way to structure micro instruction is to assign one bit position to each control signal. Okay, the straightforward way of micro instruction is assigning one bit position to each control signal. However, this scheme has one serious drawback. Assigning individual bits to each control signal results in long micro instructions because the number of required signals is usually large. Moreover, only a few bits are set to 1, means only some of the control signals are set to 1 in any given micro instruction, which means the available bit space is poorly used. So all the bit spaces are not used properly. So some of the bit spaces are used poorly. If we consider a simple processor and assume that it contains only 4 general purpose registers. Those 4 general purpose registers are R0, R1, R2 and R3. These are the 4 general purpose registers. And some of the connections in these processors are permanently enabled. Okay, only some connections are permanently enabled, such as the output of the instruction register to the decoding circuit. Okay, so for example, the output of the instruction register to the decoding circuit is continuously enabled, and both the inputs of the ALU are also permanently enabled. So these two are the examples of some of the connections which are permanently enabled. Okay. And the remaining connections to various registers requires a total of 20 gating signals. An additional control signal, the additional control signals which are not shown in that figure or means except 20 gating signals, we are having some additional control signals. Those are read, write, select, wait for memory function complete and end signals. These 5 are the additional control signals. What? Read, write, select, wait for memory function complete and end. These are the additional control signals. Finally, we must specify the function to be performed by the ALU. Let us assume our ALU will perform a total of 16 functions. Okay, so I considered my ALU performs total of 16 functions, including add, subtract, and XOR operation. In that 16 operations, we are including addition, subtraction, and XOR operations. These functions depend on the particular ALU used and do not necessarily have one-to-one correspondence with the machine instruction opcode. So finally, a total of 42 control signals are needed for a processor. So total of 42 control signals are needed for processor. If we use a simple encoding scheme, 42 bits would be needed in each microinstructions. Fortunately, the length of the microinstructions can be reduced easily. We can reduce the length of the microinstructions. Most of the signals are not needed simultaneously. So we can't use all the signals at a time. And many signals are mutually exclusive. So for example, only one function of the ALU can be activated at a time. All the functions of ALU can't be activated at a time because ALU will perform one operation at a time. So only one function of the ALU can be activated at a time. The source for a data transfer must be unique because it is not possible to get the content of two different registers on the bus at the same time. So we can't transfer the content of two different registers onto the bus at the same time. Why? Because at a time only one register can transfer the data onto the bus. And also read and write signals to the memory can't be activated simultaneously. So these are some examples. ALU will perform only one function and only one function at a time, and only one register can transfer the data onto the bus at a time. And also read and write signals of the memory can't be activated simultaneously. At a time only one signal will be activated. So this discussion will suggest that signals can be grouped. So we can group the signals so that all mutually exclusive signals are placed in the same group. So we can place all mutually exclusive signals in the same group. Thus, at most one micro operation per group is specified in any micro instruction. Then It is possible to use a binary coding scheme. So it is possible to use a binary coding scheme to represent the signals within a group. So we can use a binary coding scheme in order to represent the signals within a group. So for example, consider a 4-bit suffice to represent the 16 available functions in the ALU. So here our ALU will perform 16 functions or 16 operations. So in order to representing these 16 function, we require 4 bits. So 4 bits ranging from 0 to 15, to total 16 functions will be represented by using 4 bits. And also a register output control signals can be placed in a group consisting of all the registered output signals. So register output signals means PC out means a program counter output control signal, MDR memory data register out, Z out, offset out, R out. So, in our processor has 4 general purpose register from R0 to R3. All the output control signals from R0 to R3. R0 out, R1 out, R2 out, R3 out, and temporary register output control signals. So these all are comes under another group. Any one of these can be selected by a unique 4-bit code. Why? Because here we are having total 9 control signals from PC out to temporary register, a total of 9 control signals. These 9 control signals can be selected or can be represented by using a 4-bit code, and these all registered output control signals can be placed in another group. See here. So all the 16 operations of an ALU will becomes under one group. That group name is given as F4. And these 16 operations are going to be selected by using 4 bits from 000 to all ones. Here if we give 000 to F4 group, the ALU will perform addition operation. If we give 0001 to F4 group, then the ALU will perform subtraction operation like that. Okay. And next now we have discussed about output control signals. So output control signals PC out, MDR out, Z out, next R0 out, R1, R2, R3, total 4 registers outputs and temporary registers and offset. These output control signals are going to become under the F1 group, and these are selected by using 4 bits. From 000 means no transfer, means no control signal in is activated. All the control signals are deactivated. 001 means program counter output control signal is activated. Okay, so like in this manner, under F2 group, no transfer, program counter in, and some of the input control signals comes under the F2. Okay, so F2 group is going to be selected by using 3 bits. And in case of F3 also we are having some input control signals. MAR in, data register in, temporary register in, Y in. This comes under the F3 group and they are going to be selected by using F3 bits. Okay, so and next is one is read and write operations comes under the fifth group F5. They are represented by using 2 bits or they are selected by using these 2 bits. If we give 0 1 then a read operation is selected. If we give 1 0 then a write operation will be selected under F5. And next select Y and select 4 comes under F6 group and wait for memory function complete is comes under the 7th group F7 and it is selected by using 1 bit. At the same time end operation will comes under the F8 group. Okay, so it is also selected by using 1 bit. Okay, so in case of micro instructions, so we are grouping the control signals. Okay, some of the control signals comes under one group and other control signals comes in another group. The group naming are given as F1, F2, F3, F4. Okay, like that. And depending upon the selecting line bits, we are going to select the particular operation in that group or the particular signal, control signal. We are activate a particular control signal in that group. Most fields must include one inactive code for the case in which there is no action is required. For example, the all 0 pattern in F1. See, all a 0 pattern in F1 indicates none of the register that may be specified in this field should have its contents placed on the bus. Means no transfer means, so none of the register that may be specified in this field should have its content onto the bus. An active code is not needed in all the fields. So, and for example, F4 contains 4 bits that specify one of the 16 operations performed in the ALU. Only one operation among these 16 operations, only one operation is performed in the ALU. Since no spare code is included, the ALU is active during the execution of every micro instruction. For every micro instruction, the ALU will be always activated. However, its activity is monitored by the rest of the machine through the register Z, which is loaded only when Z in control signal is activated. Whenever Z in control signal is activated, then only Z register will be loaded with the content. Grouping of control signals into fields require a little more hardware. So for grouping the control signals into the fields requires a little more hardware because of a decoding circuit must be used to decode the bit patterns of each field. into individual control signals. So, the cost of this additional hardware is more than offset by the reduced number of bits in each microinstruction, which results in a smaller control store. Hence, only these 20 bits are needed to store the patterns for the 42 control signals. So only 20 bits are required to store the patterns of that 42 signals. So far we have considered a grouping and encoding only a mutually exclusive control signals. We can extend this idea by enumerating the patterns of required signals in all possible micro instructions. Each a meaningful a combination of active control signals can then be assigned a different code that represents the micro instruction. Such full encoding is likely to further reduce the length of microwords. So further we will reduce the length of microwords, but also to increase the complexity of the required decoder circuit. So but what we have to do, we have to increase the complexity of the decoder circuit. And next, the highly encoded schemes that use compact codes to specify only a small number of control functions in each mission instruction. So they are referred as a vertical organization. The highly encoded schemes uses the compact codes which specifies a small number of control functions. In each micro instruction, they are referred as a vertical organization. On the other hand, the minimally encoded scheme in which many resources can be controlled with a single micro instruction, which is known as horizontal organization. Okay, and next, the horizontal approach is useful when a higher operating speed is desired and when the machine structure allow parallel use of resources. So during higher operating speed and machine structure allows parallel use of resources. During these two situations, we use horizontal approach. And next, the vertical approach results in considerably slower operating speeds because more micro instructions are needed to perform the desired control functions. Although fewer bits are required for each microinstruction. This does not imply that the total number of bits in the control store is smaller. The significant factor is that less hardware is needed to handle the execution of micro instructions. Both horizontal and vertical organizations represents the two organizational extremes in microprogrammed control. Many intermediate schemes are also possible along with these horizontal and vertical organizations, in which the degree of encoding is a design parameter. So the figure which this is comes under the horizontal organization, because it is comes under the horizontal organization because it groups only manually exclusive micro operations in the same field. As a result, it does not limit any way the processor's ability to perform various micro operations in parallel. So it does not limit the processor ability in order to perform the parallel micro operations. Although we have considered only a subset of all possible control signals, this subset is representative of actual requirements. Okay, so this is about the micro instructions. So in case here we are having two different types of organizations, vertical organization and horizontal organization. So this is a horizontal organization. Here we will not bother about all the control signals. So we will consider only the signals which are activated. Okay. Hope all of you understand. Okay. Thank you.